Good morning, my dear students. In today's class, I will be discussing regarding the concept of necessary and sufficient conditions. So these are the two important optimality conditions I was talking at the beginning of this module. So why? Because so if any optimization, if any problem needs to attain an optimization, so we need to have the two important conditions that needs to be satisfied. One is called necessary and the sufficient conditions. So both the things we call it as an optimality conditions. So in today's class, let us discuss what is this necessary and sufficient conditions and how we can derive or how we can arrive these conditions for both unconstrained as well as the constrained problems and also for a single variable and multi and two variables functions. So for this, so we will let us get the conditions for both necessary and sufficient condition, and later part how we can use these necessary and sufficient conditions for solving the problems also. That also we will go to take it up. Okay. So that's the first thing. Let us start with the concept of necessary and sufficient conditions. So let us start with the first one, what we call it as a necessary condition. See, the optimality conditions are derived by assuming that we are at an optimum point and then studying the behavior of the functions and their derivatives at that point. See, any optimality conditions, when you want to derive any optimality conditions, the one important assumption what we make is we are at the optimum point. So please remember this, either whether it is a necessary condition or whether it is a sufficient condition. So when you want to derive these optimality conditions, so it will be based upon the assumption that we are at the optimum point and we will study the behavior of the functions and their derivatives at that point. So the conditions that must be satisfied at the optimum point are called necessary. This is one of the most important statement you should remember. The conditions that must be satisfied at the optimum point are called necessary. In the sense, if you state it in a different way, if a point does not satisfy the necessary conditions, it cannot be an optimum. In the sense, when we say a point, a function, a point is said to be a necessary, okay? So it has to satisfy the condition that needs to be satisfied at the optimum point are called the necessary. In the sense, if you say a point is said to be an optimum point, it needs to satisfy the necessary conditions. Okay, or you can state it in a different way. If a point does not satisfy the necessary conditions, it cannot be an optimum point. So this is the one important thing you should remember. So let us further continue. Note that, however, that the satisfaction of necessary conditions does not guarantee the optimality of the point. That is, there can be non-optimum points that satisfy the same conditions. See, when you are getting an optimality conditions for a different points or the different functions, so there may be a quite number of points, so which will going to satisfy the necessary conditions. But it does not mean that if a point satisfies the necessary condition does not mean that it is an optimum point. There may be a quite number of points which are also said to be a non-optimum, which will satisfy the necessary condition. So therefore, so it is once you say a point satisfies the necessary condition, we cannot conclude that it is an optimum point. So there should be a non-optimum points also which satisfies the same conditions. Okay, so this is very important. So in the sense, finally, what we can conclude here is there will be two types of points. One is called an optimum as well as non-optimum. Both optimum and non-optimum will satisfy the necessary condition. Okay. This indicates that the number of points satisfying the necessary conditions can be more than the number of optima. This is what we say. So only a few points can be considered as an optimum point, okay, and few will be considered as a non-optimum. So therefore, the number of points satisfying the number of conditions, satisfying the necessary conditions can be more than the number of optimum points. Points satisfying the necessary conditions are called the candidate optimum point. See, if you say a point which satisfies the necessary condition, it cannot be directly called as an optimum point, but it is a candidate optimum point. Means it is a candidate for the optimization. So therefore, you should be very careful. The necessary condition is the mandatory condition that the point should satisfy for optimality condition, but not necessary that it should be an optimum. Okay, but for all optimum points, it should satisfy the necessary condition. We must therefore perform further tests to distinguish between optimum and non-optimum points, both satisfying the necessary conditions. So means now we want to distinguish the optimum points from non-optimum points. So in a domain, you might be having an n number of points. All the points might be satisfying the necessary conditions. But out of that, only few points will be a candidate for the optimal point, and the remaining are non-optimum. So on what basis we can distinguish which is an optimum candidate optimum point and which is a non-candidate optimum point? So for that, we have a further test that means the test means so for the conditions, what we generally call it as, that needs to be satisfied by all these optimum points for means necessary on candidate optimum points, then only we consider them it as a optimum point. Okay. So this is regarding the necessary condition. Next comes the second optimality condition is a sufficient condition. If a candidate optimum point satisfies the sufficient condition, then it is indeed an optimum. In the sense, if a point satisfies the necessary condition, it is said to be a candidate optimum point. Okay. If that candidate optimum point satisfies the sufficient condition, then it is said to be an optimum point. So please remember this. So if an optimum point, if you say it is an optimum point, it should satisfy both necessary as well as the sufficient conditions. But there may be some points which will satisfy the necessary condition but not sufficient condition. So such points in the domain we call it as a non-optimum. If the sufficient condition is not satisfied, however, or cannot be used, we may not be able to conclude that the candidate design is not optimal. This is what I was talking. Our conclusion will depend on the assumptions and the restrictions used in deriving the sufficient condition. Okay. Further analysis of the problem or other higher order conditions are needed to make the definite statement about optimality of the candidate. In the sense, so we might be having, we'll be discussing with the first order and second order optimality conditions, both necessary as well as sufficient. So how we can conclude or further analysis, how we can define the statement about the optimality candidate point we will go into. So ultimately, the final conclusion here is, if you say a point is an optimum point, it has to satisfy both the necessary as well as sufficient conditions. So this is the one important thing you're supposed to remember. If a point satisfies only, so I think we have certain conclusions at the end here. So I will just list it out one by one, the conclusions here. Optimum points must satisfy the necessary conditions. Points that do not satisfy them cannot be an optimum. Please remember, these 4 points are very, 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 very important for you to go for further understanding. Right? Optimum points must satisfy the necessary conditions. Points that do not satisfy them cannot be an optimum. Okay. Since there may be some points which satisfies the necessary, I might not be an optimum point. A point satisfying the necessary condition need not to be an optimum. That is, non-optimum points may also satisfy the necessary conditions. Please remember this. This is very important. Okay. And non-optimum points may also satisfy the necessary condition. A candidate point satisfying the sufficient condition is indeed an optimum. Okay. So candidate point in the sense the point which satisfies the necessary condition. If it also satisfies the sufficient condition, then it is indeed an optimum point. If the sufficiency condition cannot be used or it is not satisfied, we may not be able to draw any conclusions about the optimality of the candidate point. So this is a very important thing what we're supposed to remember. In the sense, if a point satisfies only necessary condition and if it does not satisfy the sufficiency condition, then we may not be able to draw any conclusions about the optimality of the candidate point. So this is the 4 important points you're supposed to remember. Okay. So now let us start getting into the conditions. What are those conditions? So these conditions will be differ for single variable function or 2 variable functions, and how we can use this for getting an optimality conditions for different problems. Also, we will go to discuss. Okay. So hope you people are following. So if you have any clarifications, please make a note of these points, and at the end I will give another 4 or 5 minutes time for you to have an interaction. So if you have any clarifications, any doubts in the slide, so please note on the slide number also. So we will just go back and we will go into discuss. Okay. Now, the optimality conditions for unconstrained problem. So let us start with an unconstrained problem. Later onwards, I will take you for constrained problem. Okay. So necessary and sufficient conditions for unconstrained optimization problem defined as minimize f of x without any constraints on. So unconstrained means the function does not have any constraint. Okay, so what we call the necessary and sufficient condition for unconstrained optimization means minimize f of x without any constraints on the domain x. Such problems arises infrequently in practical engineering applications. In the sense, unconstrained problems are very rare, very rare. So very infrequently. So it is very rare you will go to see this kind of unconstrained problems in our practical engineering applications. However, we consider them here because optimality conditions for constrained problems are a logical extension of these conditions. So if they are very infrequent in practical engineering applications, then you may ask, why do we need to derive the conditions, optimality conditions for unconstrained problems? So because the optimality conditions for constrained problems are the logical extension of the conditions for unconstrained problems. In the sense, so once you know how to get the optimality conditions for unconstrained problems, and we can extend it logically, so that will constitute for the optimality conditions for a constrained problem. So therefore, first let us understand what are the conditions for what are the optimality conditions for unconstrained problems. Later onwards, we will just extend it for a constrained problem. Okay. In addition, one numerical strategy for solving a constrained problem is to convert it into a sequence of unconstrained. So another one strategy for solving any constraint problem is to convert the constraint problem into a sequence of an unconstrained problem. Okay, converting a constraint problem into a sequence of unconstrained problems, then we'll going to get what is the optimality conditions for a constraint problem. Thus, it is important to completely understand the constraint optimization, unconstrained optimization. So this is just an introduction. Yeah. The optimality conditions for unconstrained or constrained problems can be used in two ways. They can be used to check whether the given point is a local optimum for the problem. They can be solved for local optimum point. In the sense, the conditions what we are arriving, the optimality conditions, both necessary as well as sufficiency conditions for both unconstrained as well as for constrained problems. So we can make use of these conditions in two different ways. One is they can be used to check whether the given point is local optimum for the problem. Okay, and they can be solved for local optimum points. So two different ways we can use these optimality conditions for both unconstrained as well as for constrained problems. A point satisfying the necessary condition is simply a candidate local minimum. The sufficient conditions distinguish minimum points from non-minimum points. This is a very important thing, final statement, what we're supposed to remember. In the sense, so please remember, the optimality conditions can be used to check whether the given point is a local optimum for the problem, and they can be solved. The conditions can be solved for the local optimum points also. The concepts related to optimality conditions. The basic concept for obtaining local optimality condition is to assume that we are at the minimum point x star, and then examine its neighborhood to study the properties of the function and its derivatives. So please remember here, the concept of obtaining the local optimality condition is just assuming that we are at the minimum point x star. In the last class, we were discussing about local minima and global minima. So here, so when we start obtaining the local optimality conditions, so we will just assume that we are at the minimum point x star, and then we will examine its neighborhood to study the properties of the function and its derivatives. The definition of a local minima is used to derive the optimality conditions. So in the last class, we were discussing regarding the definition of both local as well as global minimum. So the definition of local minimum is used to derive the optimality conditions here. So please just revise the thing what we discussed in the last class. Since we examine only a small neighborhood, the conditions we obtain are called local optimality conditions. Okay, so since we are studying the behavior or properties within a very small neighborhood or small vicinity, so the conditions what we obtain are both necessary as well as sufficient, we generally just we term it as a local optimality conditions, because we are assuming the minimum point at x star and we are studying the properties of the function and its derivative within a small neighborhood. Therefore, these conditions what we obtain, we call it as local optimality conditions. So let us start with, let us take x star be a local minimum point for f of x. X star is considered as a local minimum point for f of x. To investigate its neighborhood, let x be any point near x star. Please understand very carefully. I will go slowly, not an issue, because it is mathematical statements, and you should be very careful while you are understanding this. Okay. Let us take x star as a local minimum point for the function f of x. And to investigate its neighborhood, let us take x be any point near x star. Okay. Define the increments d and delta f in x star and f of x star as d as it is a small increment. D is equal to x minus x star, and delta f is equal to f of x minus f of x star. Means when you just give a small increment such that d is the increment, d is the x minus x star, and delta f is the f of x minus f of x star. So these are the terminologies you should remember. Okay. Since f of x has a local minimum at x star, since f of x has a local minimum at x star, it will not reduce any further if we move a small distance away from x star. This is a very important step. In the sense, the function is having, so we have assumed x star as a local minimum point for f of x. And since f of x has a local minimum at x star, it thus value of f of x will not reduce any further if we move a small distance away from x star. Therefore, a change in the function for any move in the small neighborhood of x star must be a non-negative. It must be a non-negative. That is, the function value must either remain constant or it must increase. So this is a quite statement difficult to understand, but this is how we have to go because there is no other way in any textbook will explain much simpler than this. Okay? The change in the function for any move in the small neighborhood of x star must be a non-negative. That is, the function value must either remain constant or it must increase. That is delta f, what we are talking about. Delta f should be either it should be a positive or it should be equal to 0, but it cannot be a negative number. That is what they are saying here. So this condition also obtained directly from the definition of local minimum can be expressed as the following inequality. So we are getting the same thing, the same what is there in the word. Now we have put it in the form of a mathematical expression. Delta f is equal to f of x minus f of x star should be greater than or equal to 0. In the sense, even a small movement of x within the neighborhood of x star, so the function that is f of x should be a non-negative number. It should be a non-negative number. Either it should remain constant or it should increase for any small changes in t. The inequality in the above equation can be used to derive the necessary and sufficient conditions for a local minimum point. So the equation A, what we have written here, this equation is the most important equation for us for deriving the necessary as well as sufficient conditions for a local minimum point. Please remember this. So any change in x within the small neighborhood or a small vicinity of x star, the function f of x should be a non-negative number. It should be either constant, it should remain constant, or it should increase. Anyone, it cannot be decreased. This inequality is holds good for change in the function. Okay. Now, since d is very small, okay, we can approximate delta f by Taylor's expansion at x star and derive optimality conditions using. In the sense, what it says here is, so since the increment, so because we are talking about a very small neighborhood or small vicinity of x, and since we just move a point from x star to x, okay, so the difference, that is increment d, is very small. So therefore, we can approximate delta f or change in the function by Taylor's expansion at x star and derive optimality conditions using it. So this is what we will going to do it in the next steps. Okay. So please remember equation A. This is very important for us. Very important for us. Equation A. So here we are getting the condition where we will go into derive sufficient and necessary conditions for the local minimum optimum. Let's move further. Now, the actual concept will start now. The optimality conditions for functions of a single variable here. I am taking about a single variable. So we are doing it for an unconstrained problem. Please remember here, unconstrained problem for a functions of a single variable. Okay. So since it involves only one variable, so we generally term it as a first order necessary condition. So which is there in the green color, you can see the first order necessary condition. Okay. Let us first consider a function of only one variable. Taylor's expansion of f of x at the point x star gives. I think when I was talking in the Taylor's expansion previously, I think I have we have derived this equation, we have arrived at this equation. F of x is equal to f of x star plus f prime x star d plus half into f double prime x star d square plus r. So this is the Taylor's expansion series for a single variable. So please go back to the things what we discussed for a Taylor's expansion and please look at it how we have written the Taylor's expansion for a single variable. Okay. So where R is the remainder containing higher order terms in D and primes indicates the order of the derivative. So the primes in the sense here, so single prime, double prime, f single prime of x, f double prime of x. So f single prime means it is a first derivative, double prime means it is a second derivative. This you have to understand like that. Okay. So single derivative, so if it does not have, it is not a derivative. Single prime, first derivative, double prime, it is a second derivative. So this is what we have represented the Taylor's expansion series for a function of only one variable. Okay. From this equation, the change in the function at x star, that is delta f is equal to f of x minus f of x star is given as. What happens when we say, so delta f is what? F of x minus f of x star. Okay, so here we have written f of x. So now when you want to get delta of f of x is equal to f star. So in that case, f of x star will going to be subtracted here. So therefore, f single prime x star into d plus half into f double prime x star d square plus half. So this is what we will going to get. We'll take this as equation number C. Okay. Now, the inequality in equation 1 shows that expression for delta f must be non-negative, should be greater than 0, because x star is a local minimum for f of x. So that's what we were talking about. Since d is small, the first order term f star x star, f prime, f single prime, x star into d dominates the other term. It dominates the other term. So therefore, delta f can be approximated as delta f into f prime x star into d. See, when you look at this equation here, in this equation, since d is very small increment we have given for a point. Okay, since d is small, so what happens to d square? The product of two small numbers will become the smallest number. And also this is the second derivative. So therefore, this entire term of into f double prime x star into d square will become very small compared to the first term f single prime x star into d. Okay. So what he is saying here is in this statement, since d is small, the first order term F single prime X star D dominates the other term. So therefore, delta F can be approximated. We are approximating in the sense we are neglecting the terms from half F double prime X star D square from onwards. In the sense we are writing delta F of X is equal to F dash X star into D only because this is the term which will going to dominate over the remaining terms in the series. This is what since D is very small over here. Note that delta F in this equation can be positive or negative depending on the sign of the term F dash X star D. In the sense, so the delta F. So what we have got, the change in the delta F, this value. So since all these terms are neglected here, so this delta of F of X will depends upon the sign of the first term, F prime X star into D. Okay. Since D is arbitrary, a small increment in X star, it might be positive or negative. So D can be either positive or negative. We don't know. Okay, because it is an arbitrary value. Therefore, F dash X star cannot be equal to 0. The term F dash X star D can be negative. Is what we say. Means, therefore, if F dash X star is not equal to 0, then D can have either a positive or negative value. If X dash X star is not equal to 0, the term F dash X star D and hence delta F can be negative. So you can have a negative because if D value is negative and see in this expression, so I'm talking about this one here. Okay. So if D can be a positive or negative and this term is not equal to 0, not equal to 0, okay, then delta F and this value can have any value of negative. Okay. So therefore, to see this more clearly, let the same term be positive. Let the term be positive for some increment D1 that satisfies the inequality in equation 1. What it says is, so to understand that what we are talking clearly, let us take that the term that is F dash X star is a positive for some increment D1 that satisfies the inequality. If this term is positive, okay, so D1 is positive means delta F is also equal to positive, which is greater than 0. Since the increment D is arbitrary, if the increment D is arbitrary, it is reversible. So in the sense, positive value can become negative value. So D2 will be assumed it as a minus D. Is another possible increment. So initially, we have taken D1, D as a positive, and hence everything has become greater than 0. So now, if D becomes negative, so the negative value will go to represent it in the form of a D2, which is equal to minus D1. For D2, delta F becomes negative, which violates the inequality in the equation A. Thus, the quantity F dash, it is F dash X star D can have a negative value regardless of the sign F dash X star unless it is 0. Unless it is 0. The only way it can be non-negative for all D in the neighborhood of X star is when F dash X star D is equal to 0. This is very important condition you're supposed to remember. Okay. See, the quantity F dash X star into D can have a negative value regardless of F dash X star. F dash X star can be positive or negative. Okay. So if D is positive or negative, depending upon that, the value will become positive or negative, or it can satisfies the inequality or not. So therefore, the only way the non-negative for all D in the neighborhood of X star is when f dash x star into d is equal to 0. This is a very important thing you should remember. So this is a one important condition for us. The first derivative of x star into d should be equal to 0. This equation D is very, very important for us. Next comes stationary points. Equation D is a first order necessary condition. So this is the first order necessary condition for us for the local minimum point f star. It is called first order because it only involves the first derivative of the function. So that is if single prime is there. So therefore we call that as a first order necessary condition. Note that the preceding arguments can be used to show that the condition equation D is also necessary for local maximum point. So you can show it for maximum point also. Therefore, since the point satisfying equation D can be local minima or maximum or neither minimum or maximum, they are called stationary points. The points which satisfies equation D, we call that as stationary points. They are called stationary points, and the points which satisfies this condition, they said to be the necessary conditions or the first order necessary conditions. Okay, so this you have to very careful, you have to understand. Okay, so I will stop at this point. I will be going to not an issue forward because you have to understand the things carefully. So I will take the sufficient conditions tomorrow. Just you can look at necessary conditions tomorrow's class also, and later on I will take for sufficiency conditions tomorrow. Okay. So if you have any clarifications, guys, you can have a clarification with me. Yeah. Anybody have any clarification till now? Because basically it is a mathematical subject. There are so many statements, so many things you have to understand. You have to note down the things and please look at this. And I will be posting all these PPTs in your Google Classroom. So please follow these things. Okay. My students, do you have Jasbir Arora book with you? No. Sandesh? Sandesh, can you hear me? Can you hear me?
Hello.
Sandesh,
Yes,
can you hear me?
Yes, sir.
Do you have Jasbir Arora design textbook with you? Jasbir Arora.
Sir, SS Rao is that, sir?
SS Rao is there. SS Rao only for few points. But yes, Jasbir Arora is there. You can download from a PDF drive. Jasbir Arora.
Okay, sir.
You can look at that design of optimization by Jasbir Arora. That is a very good book for you. Almost all the portions will cover. Only few chapters will cover in SS Rao also. Okay, you will get a soft copy of Jasbir Arora. No problem. If you don't have, you just put it in a WhatsApp. I will send the soft copy also. No problem. Okay.
Okay, sir.
Okay. So please start preparing. So I will meet you tomorrow.